Hey everybody, this is Michael from Barton Musical Circuits, and this is the 12-stage JFET phaser schematic. We're going to start with the audio input, which is this wire pad here marked in, and it branches off into two spots. This 220K is going to our input mixer, where it is getting mixed with our resonance control, which also comes in on a 220K resistor here. Here's the resonance up here, which we'll get to later. And then the other branch is going to our blend, which it's a little hard to see, but that's the very thin green line on the bottom. And that's going all the way over here to a mixer stage for the blend. This op amp over here is an inverting op amp stage that's set up as a mixer, and we can see that it's 100K in the feedback path, so this is going to be half gain, or a little less than half gain, because these are 220Ks on the input, not 200Ks, and this 100 picofarad cap that's parallel with the 100K, that's there to just filter out some of the very, very high frequencies, and that's to make sure we don't accidentally oscillate at some super high frequency and put a lot of strain on the system that doesn't need to be there. And moving on from that, we have these four identical stages of phaser. So each of these stages has an input that gets split off into two ways. One goes through this 10K into the inverting input, and the other is going through this 0.1 UF cap to the non-inverting input. The 0.1 UF cap also is connecting to this network down here, which we'll go into how that works later. But for now, you can think of this as, you can ignore everything but this resistor to ground. And so you would recognize that as being a passive high pass filter there. So the net effect of having this high pass filter and this regular input in a differential stage like this is that we have an output that has the same amplitude across the frequency range, but the phase itself is going to shift at some point, which is determined by where our high pass filter's corner frequency is. And this gets repeated 4 times, and each of these looks the same. And eventually it goes to this wire pad 1, which is a connection to our other circuit board. This is split up into 2 circuit boards. And on the other circuit board, you can see that it is just 8 more of this exact same pattern. And that ends up going to this wire pad number 2, and wire pad number 2 ends up over here, which is the return to the main board. And that connects to this 0.1 UF capacitor here, which is a DC blocking cap. We're using JFETs, which are going to cause a tiny little bit of a DC shift, which within enough of these stages might be a massive DC shift at the end, especially because we're going to be amplifying it. And so we have this 100K 220K combo here on this op amp on the output, and that is like the exact reverse of what we had on our input. So we're just making up all the gain we lost from attenuating before going to the input. This output is also being sent to our blend control. So the blend is just our output of the phaser mixed with our input. The 47K is there to make sure that the output is equal to the input. If you just mix them together, you'd actually have double the strength at a lot of frequencies. This op amp stage also goes up and way back to the beginning where our resonance control was. So we have a 2.2K resistor going into the top of the resonance control. And then this is just acting like kind of like a regular volume pot with the other end grounded. And going back to our input mixing stage, it also is hooked through this 10K to these 2 red LEDs. And these red LEDs are here to limit the amount of signal that can get sent back to the input. This is creating a positive feedback loop by having this resonance control, and that can very quickly become just massive oscillations with, which can be useful in synthesizers and electronic music. But I wanted it to have the control reined in. This 10K would be a value you could monkey with a little bit if you're building this for yourself. If you wanted to have a little more oscillation. And I don't know if I mentioned it earlier, but the reason we're attenuating this is to have a smaller signal so the JFETs don't have to attenuate as much when they are working as a filter, that they're going to be more linear the smaller the signal that they're dealing with. So speaking of the JFETs, let's go to how they work. I have a sort of strange CV control for our JFETs. So this little network here that I'm circling, this is creating the voltage that's going to get sent to all the JFETs, both on this board and to the other board. This wire pad 6 is connecting it to the other board. When I first tried this, I had set it up like just a regular mixing stage, and I realized that the control voltage didn't work quite how I wanted it to, and I ended up with this kind of strange setup here where we have a differential amplifier. Our manual control is going from 12 volts to ground, and it's hooked up backwards. So as you're turning it up, it's becoming more grounded and less positive. And because we're going into an inverting input, that means that when you have this control turned all the way down, it's going to be 12 volts going in here and then negative 12 volts going out here. It's hard for me to write with the mouse. And as you're turning it up, it's going to be getting closer to ground. And the reason we want this is the way the JFETs are going to work. The lower the voltage to them, the less resistance they're going to have. And that is going to make the high pass filter's frequency go up. But our control voltage, we're expecting it to be a more positive voltage to create a higher frequency. So we just wanted to have the opposite of what that other one worked as. So this is going into our positive input with this 100K resistor to ground and this 100K input to it. So it just works like a regular differential amplifier. So this voltage that's coming out of the op amp is getting sent to all of these, and through each one, it's going through a 470K. The 470Ks each connect to the gate of each JFET, and that's providing a bias voltage. And to make it a little more linear and have less distortion, we use another 470K to bias it so the gate and the source aren't too far apart from each other. So whatever voltage here is up here and whatever voltage is down here, you're going to get the very split of that, the exact middle going to the gates, which helps linearize things and make things less distorted. The drain is just going straight to ground. So this is as our voltages get closer to ground here, they're also going to get closer to ground up here as more of the signal is getting drowned out. This 100K goes in parallel with everything, and that's just kind of setting the max resistance for each of these JFETs. Then the only thing we haven't really covered is the power. This 3, 4, and 5 is providing power for the other circuit board. Other than that, it's my standard 10 ohms, 10 UF, forming a low pass filter, and then 0.01 UFs everywhere. So yeah, if you wanted to mess with this for yourself, the 10K around the resonance, that's a fun way. That'll have an effect. The values here around this op amp, this 100K in the feedback path, that would make a big difference on your range of frequencies. And then it would be tedious, but you could also replace these capacitors here, and that would have a big effect on the range. If you wanted to have higher frequencies, I didn't want it to be like getting totally ear splitting highs on this thing, because I had a headache one day working on it. But yeah, hopefully that shows you how this works. Yeah, thank you for watching.